Moving to declustering. We're going to start with cell declustering. Let me run the cell first and then I will explain. So within this cell, we are looping over the domains. We are initializing a rmsp.DeclusterCell object. This object will handle the cell declustering. The decluster cell takes several arguments. The seed number is used to define the locations because we have to randomize the origin of the cells. Only 2D option will allow us to treat the data as if it was a 2D dataset. Drill holes as points. If this is set to true, then the centroids of the drill holes are used for cell declustering. Spatial duplicates tolerance. If we use this argument, we will consider the spatial duplicates to be a single data and not multiple. Number of origins. Cell declustering needs to define a grid of cells, and the results might be sensitive to the origin of that grid. So in order to perform cell declustering, we need to specify multiple origins and average the results overall, the origins considered. The starting place is random, therefore the reason for the seed number. We also have Y anisotropy and Z anisotropy. This controls the ratio between the size of the Y dimension against the X dimension. So if you want the cells to have the Y dimension twice as big as the X dimension, then we change the anisotropy to 2. Once the declustering object is initialized, we have access to all of its methods. The first method that we're using here is the cluster over range. This method will allow us to evaluate over different cell sizes how the average of the selected variable is changing with the size of the cell. This method will take the data, in our case the soft composites, the variable, in our case the gold. We can specify how many cells we want to test. The default is 25, we are using 30. We can specify what is the minimum cell size that we want to test. In our case, we're using 10. And we can also specify the maximum size of the cells. In our case, we are setting it to 200. There are 2 extra arguments in here. We could limit the global weight to a certain number. This will filter extreme values from the overall weights. We can also do that not global, but by drill hole ID. These limits are specified by the percentile or a probability cutoff that is specified. So if we want to cut all the weights above the 99 percentile, we can specify 0.99. If we don't want to specify a lower limit, we can leave that as known. Otherwise, we could specify a lower percentile for the minimum weight. Once this line is run, the class or object will store all the results. If we want to visualize the results, we can use the method .plot. This method is the method that is generating the plots that you see below. We are creating a figure with 2 axes, and for each one of the domains, we are populating each one of the axes. So the first one is for the outside domain, and this is how the curve looks like. The second one is for the inside domain, and this is how the curve looks like. Another element of the cell that I haven't talked about is this dictionary, cell sizes. We can select a cell size after looking at the results. For now, it's already set to 150. So you can see how the selected cell size for the outside domain was 100 and the inside domain was 50. But we could change that, for instance, to 150, and it would select a different cell size. Let's go back to 100. So once we are happy with the cell size selection, we use the same object to actually perform the declustering using the method decluster. For this method, we require the data, the variable, and the selected cell size. The result of this call is an array of weights, which we store into our soft composites. So if we look at one of our soft composites, we should see the weight column in that data set.